Hello, my friends. This is Dr. Mohamed Nezami again with another lecture on RF and microwave circuit designs and modeling. And today I'm going to talk about Orthomode Transducer designs, OMTs, abbreviated and known commonly by, and polarizers as well. So we're gonna take three cases of designs of orthogonal or orthomode transducer. Two of them are based on waveguide technology, and well, the three of them all are based on waveguide technology, Ka band, Ku band. However, we will be talking about two classes of OMTs, as I will be showing in a minute. Okay. Now, again, just to remind you, I'm an independent consultant. I can design things remotely for your company or your organization at a very reasonably rate. I operate out of Jordan with 30 years of experience in the US with several 500 Fortune companies in my portfolio. You can check my LinkedIn site. You can contact me via this email, or you can call me at this number. The number is also accessible from WhatsApp and Telegram. So you can actually download that app from your app store and just program it with that phone number. You can instantly make chats and free phone calls to me. So if you happen to have any design, I could sit down with you, work on the specifications, do the initial system design, be it active or passive circuits, anywhere from DC to Ka bands, the 32 gigahertz or so. And then I could turn in a design to you with some modeling files, with fabrication files, and so forth. So let's get started. What is an orthomode transducer, OTM, and what are polarizers? Or in fact, OTM is a polarizer, okay? So it's a device, it's a passive device that basically what it does, like I listed here, it's also known as by several names. One of them is polarization diplexer, okay? And what it is, it's a passive device that separates or combines signals with orthogonal polarization. That means orthogonal means they're 90 degrees apart, which means vertical and horizontal, okay? So it either can receive a signal that has, like in SATCOM signals, where you have two independent data modulations at the same frequency, one on the vertical, one on the horizontal. So what Orthomode Transducer does, it picks that signal, it gets that signal from the feed of the antenna feed, and then it separates them, it diplexes them, okay? Or it multiplexes them separately so that you can do processing and receive that signal. And an example of this is really the LNB, low noise block down converter, or your SATCOM, okay? So likewise, it can also work with two different frequencies where you can actually get two different signals that are polarized orthogonally, and you can separate the vertical and horizontal from either one of those two frequencies, okay? So just to show you this, I'm sure you have looked at it. For those of you that have never seen an OMT, you've looked at it 100 times before and you didn't realize that piece there is called OMT. So let's look at this. So this is a SATCOM terminal, okay? And we have the dish in here, and we have the feed system in here, and here's the horn that basically illuminates this dish. And there is your OMT device. You can see that the OMT device is a 3 terminal device. One of them is connected to the horn, and there is two outputs or two inputs. One is axial and one is branched 90-degree with the axial part. So really, if you, so this piece here is really this piece here. Okay, no, not the whole thing, but just this one of them. So we've got the horn, and then we got the OMT in here. This piece in here is the OMT, where this one here is the transmitter. So this is the TX, and this is the RX. Okay, so we've got a circular polarized signal that comes in here that has vertical and horizontal. Okay, it comes in and basically one of these will be a received signal that will come in here and go to the LNB here, the low noise block, and gets received without receiving the other one, completely eliminating the other one, and vice versa. If you have a signal you're transmitting in here, okay, this one here, basically you go in and very little will leak into the receive side, even though you have a TRF, which is a transmit rejection filter. What that does, it notches out basically the energy, reflects it back that way. So this is an OMT. Okay, so that's what it is. OMT can also be found in the microwave line of sight radios, where they use them either for diversity or to double the capacity. So basically what you have in here is if you have two transmitters, they could be at the same frequency, but they're feeding this OMT in here, which combines the two. Basically, it creates a signal that has a vertical and a horizontal component that are at the same frequency, okay, with two different signal informations to double the capacity, or the same information. And what in that case, what it does, it basically acts as a diversity system, okay? So having let's look again, just to enlighten you more on this. So the Orthomode Transducer, OTM, is basically a device, a passive device that is within the antenna feed system that acts as either, that basically separates orthogonal polarized signals, or it does the other way around. It separates the different polarizations. And it has several names. One of them, for instance, is polarization filter. The other one is polarization multiplexer. There's another name for it, which is just simply polarizer. And there's a polarization diplexer. So all these four names basically mean the same thing, okay? In addition to Orthomode Transducer. So now the main thing that is defining this device is really the operational bandwidth. And the operational bandwidth, like I mentioned in here, basically what it is, it's really, it has a constraint to be included between the cutoff frequency of the fundamental mode, waveguide, okay, in all physical ports, meaning the two feeds, and the cutoff frequency of the first higher order mode, okay? So for instance, if you were exciting them with TE10, the second mode would be TE20. So basically what you want to do is that OMT has to operate somewhere between the cutoff frequency of the fundamental mode to a certain safety margin from the cutoff frequency of the next higher order mode. Now, here are some pictures of OTMs, just basically from, you could go off on Google and just say Orthomode Transducers for antennas, and you can find many of these. So basically, again, like it points out here, basically, you have a horn that illuminates a dish, and you have a power amplifier or block up converter, buck, and you have the low noise block down converter for the receive. So this is transmit going this way, and that's receive going that way. And there's a filter in here to isolate to get more rejection from the transmitter receiver. And you get a variety of these. So here's another one, and here's another one. Now notice that always the feed at this point is always circular or square wave, a square waveguide. So it's either circle waveguide or a square waveguide, because that's how you can basically pick up appropriately the circular polarized signal from the sky. Okay. And likewise on the other side in here, for the OTM, this port is waveguide, rectangular waveguide, and this one is a rectangular waveguide as well. Okay. Of course, in this case, in here, really, you've got an F connector and an F connector in here. And that's basically the F connector is the appropriate connector that interfaces between this assembly and the modem, okay? So you've got the modulated signal that goes out with an IF to the buck and gets up converted and amplified. And you've got the reverse on the receive path. You've got a signal that comes in that gets down converted to an IF that goes to the modem, okay? Here's from NORSAT International Inc. They specialize in these devices and LMBs and bucks. And I just grabbed this one, which is really the KU band one that is used for SATCOM communications, SATCOM communications. Basically, the receive frequency is 10.7 to 12.7 gigahertz. And the transmit frequency is from 13.75 to 14.50. And so you can see here it is, okay? Although this one here, they have the transmit rejection filter attached to it. But the OTM really is just this piece here, okay? So this has got an E-field band, okay? And then it's got a transmit rejection filter. This is where you would feed the transmitter. And this one here is a square waveguide, you can see. This what interfaces to the horn that feeds there. So before now, let's, I'm gonna halt for a minute and then I'll come back, so. Hello again. Okay, so let's continue with OTMs. And like I was saying, basically an OTM is a passive device that gets attached to the antenna system that can either separates or combines orthogonally polarized signals. And it's very commonly used in SATCOM ground terminals, SATCOM transponders, or on the satellite itself, or in line of sight microwave links to perform either diversity or capacity increase, doubling the capacity. So let's get to today. Here's HFSs, and what we will demonstrate today basically is two OTMs, okay? One of them is this one here. So we've got one where you have, this is a rectangular waveguide on this side here, and this is a rectangular waveguide on here. And basically, this is the square waveguide on this side, okay? So a circular polarized signal comes in here. This gets attached to the horn in here. And the wave will come in and basically go in here, and there's a slot that is basically in this waveguide. There is an iris slot that basically a little rectangular slot that is designed with a specific length and width. The length is usually a half wavelength, so that it has to resonate at the desired center frequency. And that signal basically goes out of here, and then the other signal will go out here. The staircases that you have in here are basically used for matching the impedance between the square waveguide and the rectangular waveguide. So there's two of them. There's one that is for this the side, the auxiliary side, and one also that is for the axial side. The The next example we're going to talk about is a similar one, except in this case, we have the impedance matching between the square waveguide and the rectangular waveguide. In this case, is really tapered. It's tapered flare waveguide, and likewise on the sidary branch, it's also tapered in here. And again, there is also a slot within this that basically couples the received signal. So we always usually have the transmit side in here and receive side on here. And last but not least is this device in here, which is a simple polarizer. It's still considered an OMT because what it does, you can come in with two different signals in here. These are considered on this side. It acts as a square waveguide, and it has this septum, stair septum metal that is placed right in the middle. And what that does, we'll show in a minute the theory behind it. It will actually combine both of these to create either a right-hand circular polarized or left-hand circular polarized signal. And this is called, the name for this is really a step, metal step septum polarizer, okay? So let's go back to the theory and just show you how this works. So, like I mentioned, before we get to the septum, let's look at this. We're going to look at two illustration examples of OTM using HFSs ANSYS system modeling. One of them is the KU band SATCOM, and one of them is the K band SATCOM. This, for instance, for the this one here is the KA. Okay, the receive side would be this band here. Okay, like you can see here, we've got the two signals comes in. There's a horizontal one and a vertical one, and the structure of this here, you have the square waveguide in here that basically the signal gets separated into the horizontal and the vertical separately. And you can see from the size of waveguide that these two waveguides are for two different frequencies, because in this case, they are two different frequencies. Or what we could do is we could transmit a signal at this frequency here, and the signal will go out. And then the reverse side, we have a circular polarized signal where we want to pick up just the horizontal piece that comes in here for the receive band, or vice versa. Well, in this case, the SATCOM, this is really the transmit. This is the receive, okay? So that's what we have pictorially in here. We have the horn, which antenna, which gets the vertical and horizontal. The OMT is responsible for demultiplexing, not just the frequency, but the polarization as well. Because what you essentially, you have here is at this frequency, you can have both vertical and horizontal, but you want to pick up only one, for instance, which is this one here, the vertical horizontal, okay? So we have the normal names for these ports. Basically, we have a common port, always that's this one here, which is either circular or square, always. And then we have coupled or lateral or branching port, which is this port here, okay? And then we have the primary or axial. These are different names. You go through the literature, a lot of times you will find that some people use coupled, some people use lateral, some people use branching. All these names mean the same thing, okay? So this port is called usually axial or primary. This port usually called the coupled or lateral or branching, okay? So this again, just an exploded version of that diagram. So you can see that this here, when you design it, when we design it, we start out with this. We say, okay, we know the dimensions of this because we know we have the incoming frequency. So we can pick this from the AIA standards for waveguide dimensions. So this piece is designed giving. It's a natural fallout from the band that you're working, and the same thing for the branching branch here, and for this one as well. So this piece, the dimensions basically are always giving. As an EIA standard, you pick those. And then so your task is to design this piece here, okay? The piece that interfaces and matches the impedance from the square waveguide onto this rectangle waveguide. And likewise on the other side, to design a slot that couples the signal, okay, and then matches the impedance to this waveguide in here, which is the same as this. Of course, in this case, you have a bend, an E-field bend. So that's a standard design also. You can pick that. That's, you know, you can look in the literature. They give you all the dimensions for the suggested dimensions for optimal best return loss. Okay, so now, so this one with the staircasing with step impedance matching, and usually the length of these is a quarter wavelength. So this is really nothing but a multi-section quarter wavelength impedance matching, okay? Sometimes you might see some kind of iris in here to cancel out some of the impedance, the susceptances associated with the opening in here, okay? All right, so this case here, this one is, I just happen to pick this one, is a KU band, except this one, we don't use the multi-step quarter wave. We use a continuous tapered impedance transformation between the square waveguide to the rectangular one, and likewise from this piece here onto this piece here. And as you can see in here, this is a standard WR75, WR62. These are standard dimensions for this band here, which is the KU band SATCOM transceiver allocation. Now, there are varieties you can see in the literature. Sometimes the stepping is done on one side only and so forth, but, you know. Another thing that we find in the literature, the simple T-junction OMT. And that is basically designed with a piece of square waveguide and two rectangular waveguides, okay? And these here with the opening onto the sides, and you can design this, very simple to design. Of course, in the back end is shorted in here, and this is a quarter wavelength at the center frequency, the distance between this opening and the back end short, just like we did in my other videos on the waveguide to macrostrip transitions. Say likewise in here, exactly the same. So from the center point in here to this point here, that's the wavelength dimension at the center frequency. This one is simple to design, and I may do another video where I can illustrate the design of this and model using HFSs in the future. So look for that. Now, the design usually is scalable with these OMTs. So very nicely that you can start from the beginning. Okay, so you pick this dimension is given, this dimension is given, this dimension is given, because that's given by the EIA standard. So you have a KU band, you got the transmit frequency waveguide, and you've got the receive frequency waveguides. They're known, the center frequency is known, so this waveguide is picked from the EIA standards, and this one as well. That's unless you have a specific application where you really don't basically where you want to specialize design for the cutoff frequency. Now, the design, these dimensions, as you can see in here, so we've got the length of the opening in here, got the width of the opening, and this sits right in the middle of this tapered ceiling of the waveguide in here, okay, of this tapered waveguide. And you've got this length, you've got this length, and then this length. So you design them basically as a fractions of the wavelength. And once you fabricate this, by the way, the fabrication, I didn't talk about this, but usually this is symmetrical. This is symmetrical on one axis. So usually it gets designed from a brick of aluminum. So you get a brick of aluminum and you split this in half, and there's two halves. So your CNC machine comes in, carves one side and duplicates it, and then you sandwich it together and screw it tightly together, and of course, very tight tolerances. But if you design the dimensions of these with fractions of a wavelength, okay, then you can, at any point in time, you can come back to this design and scale it for another frequency. All you have to do is just substitute the new wavelength for these numbers, and you get totally a new geometry OMT. Okay. So let's go back and talk about the stepped septum polarizer. And that's a very simple design. And you find this a lot in the SATCOM transceivers. And also another area I found that many people use it in radio astronomy, in there where they're basically listening into the galaxy. And a lot of times they need to split the vertical and horizontal and detect them separately and process them separately. This one is simple. It says this: you just get a square waveguide and you place septum right in the middle. Okay, the back here is open. So you've got that metal in here comes in with steps. The length of these steps and the height is designed just in a similar fashion to designing a multi-section quarter wavelength transformer, but in this case, it's not really doing matching. Okay, so there are a lot of papers on this, how to design the dimensions of the septum, because that's all there is to design. The square waveguide, you're giving that from the EIA standard. So all you need to do is just basically come up with the length and the height of these guys in here. And this can be done similarly, you can do this in a circular waveguide. It doesn't have to be done in a rectangular waveguide. And that's how usually it's configured. So you've got the horn picking up the signal or transmitting the signal, illuminating a dish in here. You got the septum in here. You got two separate feeds in here. One is input, one is output in the back for the two rectangular waveguides, which corresponds to the vertical and horizontal. So let's look for a moment, really what happens. How does this work? I'm not going to elaborate more than this, but just to show you a little cartoon of this. So we've got a signal, either right-hand side polarized or left-hand side polarized, okay? And that's basically designated by the E field of the horizontal, the direction of the horizontal E field, okay? In this case, this one is to the left, this one is to the right, okay? You can take it as that for now. If you trace the signal from here going in and how it behaves while the wavefront gets collided with this septum, you can trace out what happens. So we start out with a very tiny height. That's the tiny height in here, all the way to where we have full height metal that acts as separates the two polarizations separately. And then you can see it in here that once you go in, okay, this component in here, the horizontal, starts getting little by little splitting until it gets completely split with 180 degrees apart, okay? And then likewise on the other side, look what happened to the vertical one. The vertical one comes in and splits all the way until it becomes basically two symmetrically halves of the E field. And now if you combine these, okay, what happens is that the lower side in here, basically this one with this cancels out because it's 180 degrees out of phase, while this one is really in phase with that one, and you get that one, okay? So that means that you got that polarization. Now, likewise, you can go in and start tracing what happens to the other polarization, and you'll see that it comes naturally, falls in the separate waveguide, okay? Now, so a lot of times, basically, how do we pick the signal from here? So we have the feed in here, like in here, for instance, we have the horn and we have dish in here. Signal comes in, and the back end is two waveguides. Now you can short them, okay, and place a pin to coaxial transition, okay, or you can leave them open. Okay, you leave them open and then attach a waveguide flange in here. So you have, depending on how you want it, that's a different way of doing it, okay? There is one piece that we didn't talk about a lot of times you see on these feeds is the interface between the rectangular waveguide and the circular waveguide, which is the horn. And there's a little piece which basically transforms the mechanical dimensions from circular to square. And that is basically it is a device that introduces just a little bit of disturbances to the E field, and you can search online in the literature and just type, you know, circular to square or to transformer piece, and you'll see a lot of that. A lot of times, of course, you've got the signals in here that is from the back end in here, those two ports. You need to design a little additional bend so that you can, it's easier to integrate with your system, because if you leave it, as you can see here, they are so close, you can't even get two flanges together on the back. So, and that's what you see in here, basically, as an example. Okay, so just, I know we mentioned this in the design of microstrip to waveguide transitions back then. This is an LMB example I just happened to pick up. And these boards, basically, all they're doing, basically, you got a septum, you got a circular waveguide and a septum in here, and you can see the steps, here they are. You can see this thing is sticking in, and what sticks out in here is a piece of metal that will act short once we have a cap that covers this. There's a cap that comes in and covers this opening, with leaving a little arc in here for this polarization and this polarization. And what this does, of course, these are for SATCOM entertainment TV low noise blocks. And so what this is doing, really, it's picking the horizontal and vertical of your favorite program. And you can see in here that it goes in and basically has separate processing and amplification and filtering for vertical and horizontal. And you've got a bunch of control circuits in here where that's where you program either horizontal or vertical, depending on which ones do you bias, this side or this side. And that's what you see in here, power regulations and biasing and all that. You can see it also in here, okay? And you can see that here's one branch and here's one branch of the low noise amplifier. This here, of course, you can see that these devices were removed. This is a junk board, but usually, like in this case in here, you get this polarization, be it vertical or horizontal. You get one amplification stage, another amplification stage, and then you got a filter, a hairpin filter, and then another amplification, then another filtering, and then you come in here, this Watkinson combiner, okay, that goes in another amplification and then goes in down to the next section, which mixes it with an LO and outputs an intermediate frequency. So there's your septum in here, which is nothing but this device here. Okay. So now, now, how do we design these things? We really design them in HFSs. So basically, we construct these on a piece of paper first, and then we enter these dimensions. And I will generate in the future one video of how we do that, how I did that. But because it takes a lot of time to get these geometries drawn correctly in HFSs. Or now you could, there are some program synthesis like this program in here, Mason, Microwave Wizard, which is from mason.com, you can refer to it. What this does, it gives you really a way to design this synthetically and synthesize it, and much easier. Okay, just a little commercial in here, and then we're gonna go back to the HFSs. So let's go back to the HFSs. Let's start out with this guy here. This is, okay, this is the KA band one. Okay, so the way I plotted this is I plotted this all as one structure with pieces. These pieces in here, before I united them, as you can see them in here, they're united in this case. So there are these pieces in here, which correspond to this piece, this piece, this piece, this piece, and so forth. And then at the end, what I did is I made them all a vacuum, okay, and unified them in one piece. That's what I did in here, okay? And when you unify them now to fabricate this, you would create this, and of course, a mechanical engineer will grab this, and he has to carve out this hollow this into a block of aluminum. Of course, you can't hollow it completely. What you do is you split it around the symmetrical axis, and in this case, this here, the ZY axis, okay? So you can put it into half, and then these two halves, it's so easy to CNC one half, and it's symmetrical exactly, so you only need to generate one half. The other half is exact symmetrical. So you mechanically design just one axial half of this, and you get the other half and you sandwich them together, and hopefully it will work. So in my case, because of simulations, what I did is I said, okay, let's make it all air, and let's come in here and define a boundary of the whole thing as a perfect conductor from the outside, as you can see in here. Okay, so it is basically, you got the opening is here. Okay, for this one here, for this this side, and there's the opening for this side for that one. And what I did now, of course, is you excite it carefully. Now, what you need to excite it, the common port, you come in here, this port here, which has the both vertical and horizontal. This one here, you need to do two modes of exciting, okay? Because this is circular, so you got one horizontal, one vertical, while the other two rectangular branches, that is this side here, okay, is basically, so this one here, okay, you got this one and you got that one there on this side. These are a single mode polarization. So, and then of course, in this case, I set the frequency, the solution for this, and from 14 to 34 gigahertz, and this is what I got. Okay, this is the return loss. Okay, for the 3 ports, and this is the transmission for one port, and this is the transmission for another port. And now, so next, let's illustrate how the E field is done for this. And now, remember this, the S parameter right now that I've got on this, because I entered these without any optimization, okay? I did not optimize it, so they're not to the best of what we want. So it's still, you get these, and then you have to tweak them with optimization and tuning until you get them right. But let's just go for the purpose of illustration, just to show you for right now how the signal really propagates in this. Let's animate this, and the first thing we want to do here is we're gonna excite this port in here, okay, and then watch at one frequency where the signal will come out, okay? So what we have is right now, if we go and check out the excitation of this, let's see, fields, fields and data sources. So let's look at this. So we've got the common port, we've got 2 modes, okay? And then we've got these two in here. So what we're going to do is we're going to common both of these first, okay? We're going to excite the circular polarization mode, and then we're going to look at this one in here. So, and now let's just animate it. And now what happened, of course, this is, let me see what frequency is this at. This is at a specific frequency. Right now, you can see the signal is leaking in both, but that's because this one is at 22 gigahertz. So let's go in and see, for instance, at 32 gigahertz how it behaves, and it will have exactly the same thing, okay? So you can see that the signal is going in here very strongly to this port. That's the transmit, okay? That's the transmit really should be the other way. So let me go back. Let's go back and redo this. So now this is the OTM. We have two polarization. One you're receiving, okay, on one polarization, comes in here, and another one we're transmitting through this port. And we want to make sure that when we excite with the transmit signal, nothing comes out of here. Because remember, this is a KKA band. So transmit in the 30s gigahertz, and the reception is in the 20 gigahertz. So it's not just separating the polarization, but it's also demultiplexing the frequencies. So let's go in here. Okay, so we need to know which port is which. So this one, let's look at the excitation. Because we coupled them. Okay, well, good thing is we named them coupled and primary. So we're gonna look at the primary first. So we're gonna come in here and go to the fields and edit sources. So we're gonna do the primary. We're gonna excite the primary to see what the transmitter does, and then this one we don't want signals on it. Okay, so let's check it now. So let's see how it behaves. Okay, so we're basically, the signal is very hot in here, and then as you can see, without even animation, that the signal is completely, as you can see, is completely going out to this side, and very little is leaking into the slot that goes into the receive path in here. Because as you can see, this side here is attached to a 10-watt transmitter in a lot of cases, and even 50 and 100. So that's a lot of signal compared to the signal here. Like this might be 40 dBm plus 40 dBm, while the received signal is like minus 110 dBm. Well, in this case, you have the antenna gain, which is about 30 dB, the parabola gain, the antenna itself gain. So you're dealing with minus 80 dBm signal and plus 40 dBm signal. So you would want at least 40 to 50 dB of isolation between these here. And that is obtainable with this design, of course. So let's animate this and just watch what you're seeing in here. So you can see that, there it is, ladies and gentlemen, see? You can see that the signal is coming in here at 32 gigahertz in this case, and going out to this port, very low is leaking into the receive side, okay? So even this one in here can still be optimized so that much lower energy comes in and leaks onto that side. So let's show this, and okay, let's show sideways so we can see it. Okay, there we go. Or we can see, there you go. So we can see it this way. And see this is undesired in this case to have any of these signals. It's getting completely rejected. Okay, so now let's go back and do the same thing. Now in this case, what we're gonna do is we're gonna go to the E field and to the field, and we're gonna edit the sources. Now I want to excite it so that I want to look at the other one. So we're gonna put 0 in here, and there is C port, which is this one here, the couple port. So we're gonna put 1 in here, meaning common one, and hopefully common one is what comes out. No, common one come out to that port, so it's the other way around. So we're gonna do field the sources. We're gonna do this one, and this is 0. Okay. Yeah, I must have done something wrong here. So let's try this again. Sources. Okay, so we are assigning common 2. This was 0. Okay, so let's. Oh, okay, here we go. Yeah. Oh, now you can see that different mode is getting excited in here. That's no good. Okay. And the reason is because we're still running at 32 gigahertz. We're not running at the right frequency for receive. So we're going to go back and run this at 22 gigahertz. And there you go. Now the signal is coming in here on this horizontal polarization, and some little bit going into the transmit side, but most of it is going into this port, the receive side. Okay. Now, so what I'm going to do is I'm going to break here, and I will create another part to this video where I will show the other one, which is we're going to show how this works, and we're going to show the polarizer, how it works. Okay. So tune in to the second part. Thank you very much. Again, feel free to drop me an email, phone, or a message. I'll be glad to help you with any designs that you might have. Okay.